Uh, Hi, everyone. Welcome to Meeting C++ Online. It's good to be here, even in this very different medium. I am wearing my Meeting C++ attire from my first Meeting C++ conference. So due to the nature of the medium and how things are set up in Remo, I prefer to take questions at the end. And let's get back on our topic of today, sanitizers. And we'll see how tools can help us make our code more solid, more robust. This is a story in 3 parts. We're gonna quickly gloss over static analysis tools, and we're gonna see in general how analysis of code and leveraging multiple tools to do code analysis will help improve our code. And the main focus of this presentation will be on dynamic analysis, and we're going to focus on the other sanitizers per se. And the third part of the talk will talk about a little bit of warm fuzzy feelings, and we're going to quickly see some direction or some workflows that can help you combine dynamic analysis with fuzzing. Let's get started. So humans have always depended on tools to make their lives easier, and having and building better tools helps you build better software. And we have tools like the productivity side of things, the blue stuff on the left, like editors and IDEs and refactoring tools and build systems and package managers. And we have your quality tools or assurance tools or coverage or robustness that guarantees quality of the products that we deliver. So things like test frameworks or profilers or static and dynamic analysis and fuzzing tools. So we'll quickly glance over some of these and see how they can really help in your day-to-day life and improve your workflows. And why do I care about this? Because we've been actually addicted to such tools. And we actually made a case study that I presented a few years back at CPPCon on actually leveraging the power of static analysis to actually tidying up a fairly old code base that is under active development, and how we built custom tools to help in this workflow. And you might know me from previous presentations relating to Clang Power Tools. So let's get started. First things first, static analysis, because this is how I got into using such tools in my day-to-day workflow. And this is where we have plenty of experience in our team in leveraging such tools to find latent bugs in our code. Just in case you didn't know, there's a CPP core guidelines checker within Visual Studio. I'm going to focus mainly on tools for Windows because that's where I live mostly. And I'm trying to showcase some of the stuff that has been brought on to the Windows platform and the Visual Studio ecosystem to help leverage these community de facto standards. And we do have a CPP core guidelines checker in Visual Studios, and actually starting with VS 16.7, we actually have new safety rules integrated and new checkers here. There are a bunch of tools and checkers here. I listed just a few of them, and you can check them by yourself later on when you get the slides. By the way, all my slides have a lot of links that you can follow and read at your leisure later on. So I'm just going to highlight some of this site investigations that you can do on your own. Just in case you didn't know, Visual Studio actually has 3 levels of static analyzers, so to speak. You have the MFCC code analysis, that is the bulk of the code checkers. It also has Clang Tidy built in, and it also has some lightweight code linters built in. I'm going to focus a little bit on Clang Tidy because this is the tool that we've explored the most in our team, and with great success, I might say. We've actually leveraged a lot of modernizations in our code, and we've actually found a lot of bugs. Some of the checks I would like to highlight, it's some of the ones that paid the most bang for the buck for us in terms of effort versus actual reward. I'm just highlighting some of them here. Some string related checks, and I'm gonna, by the way, you can actually leverage a nice GUI interface to search and learn about each individual check with inline help, and you can toggle and mess around and investigate each of them. I'm going to focus a little bit on security checks, and I'm going to pick background dangling handle here, which is closely related to string view. And it helps detect dangling references because it's very easy to shoot yourself in the foot when using string view. I have a whole other talk about that. You can watch it later on. And this is a very nice check helping finding these dangling string views attached to temporary strings. So I do encourage you to play around with this check. Also, you might be familiar with the lifetime profiler. Lifetime safety actually tries to address the same issue within the CPP core guideline checks. And it's there because it's very easy to create basically dangling by default, because it's very easy to convert a string to a string view or a vector on array to a standard span now in C++20. So things like these checks in CPP core guidelines actually help you catch some of these problems. For a while, we've had W lifetime as an experimental flag in Clang, helping us catch, for example, cases like this one, where you have a temporary that ends at the end of the full expression there, and you have a string view that's attached to it. But this is still experimental, so it's not in the mainline Clang. But we do have, starting with Clang 10, we do have a diagnostic that is actually on by default, and that is dangling GSL, and it addresses the very same thing. Its scope is a little bit different, but it addresses some of the same issues. And the good news is that it's on by default. So you should always try to cross-compile and see everything you can, even if you're not using Clang as your mainline compiler, as we do. If you want to learn more about how this stuff works, more about the lifetime profile and the checker and how it hooks into your code and actually tries to find some of the issues, I do recommend this excellent talk by Gabor and Matthias, and you can watch it later on. ClangTidy has a lot, I think over 300 checks built in, but it's organized in modules and it's easily extendable. So you can easily extend checks or modify checks or build your own checks. And this is something that we actually try to do. And you can construct matchers at the AST level and build custom checks for your source code and specific for your project, and identify stuff and even do large-scale refactorings by building such ClangTidy modules. So it's not always just about finding bugs. You can also automate refactoring tasks with ClangTidy. So I do encourage you to learn more about it and actually try to use it on your code base. Yeah, those are the fixes that I mentioned. So if you use tools such as Clang Power Tools, you can easily swap in and activate your custom ClangTidy builds or activate specific checks that you write. The important thing is, for all of this, is actually to run these checks regularly. Whether they are your own checks or the built-in ones, it's not enough to run them once. You have to make them part of your workflow. So this way you make sure you don't have recurrences and you catch new stuff that trickles into your code base. If you do want to explore further and learn how to build refactoring tools on top of LLVM, I do recommend this excellent talk by Stephen Kelly, and he also has a very nice series of blog posts, some of them on the Visual C++ blog, some of them on his own blog. Also, this very nice presentation by Fred Ingo on how to build Clang-based refactoring tools, again, on ClangTidy, and how to create matchers and test them and run them at scale. So feel free to bookmark these talks and follow them if you're interested later on. And yes, I have to plug my own talk about the same issues. Sure. Coming back to Visual Studio, we do have, starting with version 16.2, it's a bit of older version, we do have support for Clang LLVM both for MS Build and CMake based projects. So you don't have to convert your projects or anything to leverage these tools. And it actually ships with Clang CL driver if you want ease of use. I actually prefer the Clang++ driver, but this one works as well. It's very easy to set up. With 16.7 Visual Studio, you actually have the latest LLVM 10 in there, in the box. And you can easily set it up as your built platform toolset alongside your usual MSVC builds. It also comes with Clang Tidy for Clang code analysis, like I mentioned earlier, starting with 16.4. And it's, again, very easy to activate within the project property sheets. So just enable it. You'll see it in the expected ways, in the output window and the error list. And you can filter these warnings from your build stuff. You can triage them. You can tackle them one by one or by class of warning. So it's all you would expect from the usual warnings that Visual Studio issues. So in the expected place. You can actually have background checks run as you type. So you might type along in your code, and code analysis runs in the background. It shows you stuff in the editor as squiggles as you type them. So on the one hand side, it's very nice because you don't have to remember to run those checks. So it's very nice to run them in the background. But sometimes it can really throw you off from your workflow and the thing you're trying to focus on. And they tend to throw you on a side quest to address the issues. But it's nice that it points them out early on. If you're not on the latest Visual Studio 16.4 or newer, you can leverage the same tools and the same power by using Clang Portals plugin and leverage Clang Tidy and even Clang Check and Query to build your matchers. Now we're going to move on from static analysis and try to contrast it with dynamic analysis, runtime analysis. And if for static analysis, the main workhorse of compile cycle is actually an offline cycle, and it can take longer to process source code, and this is why it has the luxury to actually do more analysis that a proper compiler cycle can do. It's, of course, intimately linked to the programming language you use, so it has to know the semantics of the code it analyzes and understand what you're trying to do. But it can yield a lot of false positives, and sometimes you have to go on a wild goose chase. And I've done that before. And you investigate some issue, and it turns out to be a false positive, and you're going to spend some hours try to figure it out. And you can never know. Sometimes it's a legitimate issue, so it's always worth pursuing. But yeah, it's not always satisfying. It's usually very poor at whole program analysis, so it's very hard for it to follow connections between different translation units. This stuff is improving, but it's not by any means perfect. And it's almost always helpless around virtual functions because it's very difficult to devirtualize calls in most situations. It has weak analysis ability around global pointers. And the most difficult task, I think, is pointer aliasing, because it makes it very hard for analyzers to prove things about the correctness of the problem or prove things around access to certain memory. And it's basically a vicious cycle in terms of type propagation of inferent types and aliases analysis. So they basically depend one on another. So it's very, very difficult problem to solve in general. In contrast, dynamic analysis is sometimes intrusive because you need to compile the program in a special mode most of the time. It does incur a runtime overhead, both in performance impact, depending on the tool, from 2x up to 10x maybe. For some, maybe memory related into instrumentation, it consumes extra memory, maybe twice or more. It's difficult to map error reports in source code sometimes because of release and optimized builds. Functions are inlined, intrinsics are used, symbol information might be misaligned. It's a difficult job to map sometimes optimized builds into dynamic analysis. And let's face it, not every bug is reproducible in debug builds. Some tools require you to recompile the whole program in instrumentation mode. So this could be an issue. For example, the memory sanitizer requires this. Might be an issue for interop. You must integrate runtime analysis with test units because, as opposed to static analysis that can cover everything, runtime analysis can cover all the things that you actually test for. So if you have proper test units with proper coverage and you test all possible scenarios that you can think of, then you have a confidence that the analysis yielded the right results. But if you don't have proper coverage or proper test units, dynamic analysis won't save you. So like anything else, proper test units and proper coverage is a win. And the biggest impact is when you're combining runtime analysis with fuzzing, because as developers, it's always hard to figure out what's the exact combination of input knobs that we have to mess around with to get the crash that our users are actually hitting. So fuzzing really helps here, really testing at scale. And we're going to talk about this a little bit later on. The biggest thing is zeros, false positives, or so it's advertised. So I think this is makes it worthwhile, because everything that is actually signaled during such runtime analysis is actually an issue that is worth pursuing and worth spending hours on debugging and investigating it. So this is what pays big. And we're going to focus the bulk of our presentation actually on dynamic analysis. Just in case you didn't know, I had recent discussions with some people at CPPCon about this, and not everyone actually knew that about control flow guard. And this is a fairly old thing that is actually built into Windows. It's enforces control flow integrity, and it actually works as a complement to ASLR and data execution prevention. And it has been in MSPC for a while now, but the news is that control flow guard is now supported in LLVM 10. So Microsoft actually contributed this functionality back to LLVM, and it's available for C++ and Rust as well because of this. So big win here. But that was a side story, and we have to go back to talking about our sanitizers. And we have a bunch of them. We have the Agile sanitizer, the leak sanitizer, thread sanitizer, memory sanitizers, and of course our preferred undefined behavior sanitizer. I'm going to focus today on Agile sanitizer because the big news is around this, because it just recently got ported to Windows, and it's a big win for actually ensuring quality for our applications. In a recent survey that I've actually seen results of, run by Meeting C++, we actually see that people use sanitizers a bit, but the most worrying part about me is that some people are not using sanitizers at all, and I'm guessing this might be people that are not on cross-platform projects, so are maybe exclusively on Windows, or on platforms that don't have these tools. And I'm hoping that after Agile sanitizer becomes, and later on maybe other sanitizers become ubiquitous on all platforms, maybe more people will actually be in these other columns, and everyone should at least know or aspire to run some sanitizer on their platform. Because a common vulnerability and exposure problem is memory safety issues. So again, even in 2020, over 70% of root cause of CVEs are actually memory safety related issues. So this is a common problem, and a problem that is addressed by all major platform builders, and it's an ongoing concern that other languages are trying to address, that platforms are trying to address, that runtimes are trying to address. So even browsers are trying to address this. So it's a big issue. Address sanitizer actually is a de facto standard for detecting memory safety issues. So it's important for correctness of our program, and sometimes for true vulnerabilities like CVEs. So it's not always about security, but sometimes it's actually about building a robust application that doesn't crash and frustrates our users. And it can detect usual suspects like use after free for dangling pointers, heap buffer overflows, stack overflows, global overflows, use after scope or return, initialization order bugs, and even memory leaks sometimes. So all around good thing. And we'll have to dig into it. It started in LLVM by a team at Google and quickly took off a de facto industry standard for runtime program analysis. And it has some time in the wild. So it started in 2012 in LLVM, quickly was adopted in GCC, and in late 2019, we had our first experimental implementation starting to show up in MSVC. And we'll see what we can leverage on Windows. Starting with 16.4, so last October, we actually have the first implementation on Windows, and it was announced at CPBCon last year. And Jim Redigan actually gave us a sneak peek on how it works and the features that are down the pipeline. And today, we're going to see some of those things announced actually came to fruition, and we're going to see some of the issues, and we're going to see more stuff that's coming in the next versions. So stay tuned. It's very easy to enable from the Visual Studio installer. When it started in 2019, you just get the 32-bit instrumentation, and you can actually instrument just for release builds. So that was a bummer, but we could play with it and see the technology preview and report bugs and get a feel for how it might work and how it could fit this into our workflow. Very recently, this summer, we actually got a major release update in 16.7, and we got instrumentation for 64-bit builds and both debug and release builds. So now we're really prepared to take this on and actually test it on our projects, and that's what we did. And I'm here to report back. We do have support for all debug runtimes, both static and dynamic linking, and both architectures. So 16.7 supports these Asan features, usual things you might expect. I'm not going to read all of them. We're going to see some examples in later slides. And things to come. We already have a preview build of Visual Studio 16.8, and some of the stuff coming in the preview build is support for global C variables, which are a whole different beast to tackle. We have options to actually opt out of the other sanitizers in some sensitive parts of our program. I won't go into details there. And automatically link appropriate Asan libs, which sometimes is a hassle in the current implementation. And in the future versions, we're going to have an opt-in, because it's costly, opt-in into use after return check. And like I said, preview 3, as we speak, during Microsoft Ignite, we had another preview released, 3.1. So we have lots of good stuff coming. I do recommend that you watch this presentation from CPPCon, where Sai and Marian actually go and cover full breadth of all the good things that are coming in this build of Visual Studio, all the latest and greatest, from ISO C++ conformance for C++20, all the way to productivity features. So I do recommend that you watch this talk as soon as it becomes available online, maybe a week most. Asan is still experimental, so it will very soon come out of beta, and they actually need our help to report bugs. I've found bugs and I've reported bugs, and you should do too. You should try it. You should kick the tires and see how it works on your project, or maybe play around with it in some toy project and actually report bugs, because it's a very difficult thing to get right, and we'll see some of the challenges there. It's a very tall order to bring Asan to Windows. People might laugh and say that it took Microsoft over 8 years to make this available on Windows. But it's actually a very hard thing to do, because the surface area of the Microsoft platform is enormous. You have a lot of non-standard C++, and yes, MSVC has to compile all this code and has to work with the Asan runtime. You have your structured exception handling. We actually have a lot of this in our project. You have your AV traps and AV filters. We have that now in our project, so it's not just horror stories. People actually use this stuff. There's a vast amount of legacy code. I mean, really, really, really old code. So it's very hard to make sure that it works with some very ancient constructs that are very, very non-standard C++. And you have the elephant in the room. You have COM, and COM is still a big player on the Windows platform, and all the modern Windows is built on top of COM. So you have the COM legacy layers, and you have the new COM, and it all has to compile with the Asan runtime. You have managed C++. Yes, that was the thing, and it still is. Some projects actually do interop in this way. And you do have runtime interop issues with the Asan runtime and the .NET managed code. So you have to make that work in your project. So Windows platform is a very mixed bag, all kinds of things. So they all have to work somehow, because otherwise people will complain that, hey, you have these nice nifty features, but it doesn't work for my project. And on this occasion, I'd like to say a big thank you to the Microsoft team tirelessly working on this. And the reason I say that 2020 is the year of sanitizers is because we finally have at least for Asan, we have it on all the platforms, on the main platforms that we're actually trying to target. And everyone will continue to invest heavily in this area of sanitizers, just because they're so effective at finding correctness issues. So Microsoft has contributed back to LLVM all the work they've done to make the Asan runtime work on Windows, and they're continuing to do so. And they're gonna contribute back all the work they do around global C variables. And the whole community is basically coming together behind this effort, and we're going to see tremendous advances in this area, and we're going to see more sanitizers coming to the Windows platform, hopefully soon. And I think this is the first year that things are starting to come together, because up till now, if you're not on a cross-platform project and you want to buy into these tools and try them out, you're out of luck. In terms of workflow, Asan Visual Studio integration actually has support for both MS Build and CMake type projects, both for Windows and Linux targeting from Visual Studio. So you don't have to convert your project or anything. If you have a CMake project, that's fine. If you have an MS Build project, that will work as well. So activating it on both projects is just very easy, one click. Debugger integration for MSVC and Clang LLVM compilers. I think this is a big win on the Windows platform. The debugger integration is absolutely fantastic, and I think it will improve over time as well. This is a sneak peek how it would look. For example, here heap buffer overflow you have your contextual error right here in the exception window with all the details, and you can drill down more and investigate the issue. So it's the IDE exception helper, and it's very contextual, and it actually gives you all the information that you need to drill down into and see how you can investigate the crash. As you would expect, the raw output from the other sanitizer is in the output window, and it has the usual appearance that you see on other platforms. The big thing here, I think, and I think it's a game changer in general, not just in terms of ASAN, because this is actually useful in many other situations, is actually the snapshot file that Visual Studio supports. And it's actually a mini dump file that the Windows snapshot process makes, and it captures virtual memory on your heap, plus a lot of metadata about your program. And Visual Studio can actually parse and open this, and you can pinpoint into your exact location with symbols into your code. And it actually, basically, aside from ASAN in general, it actually can change the way you actually report bugs. Because if you encounter such a crash or a problem, you can easily save such a mini dump file and attach it to an issue or share it with someone, and they can immediately go into the exact point that you were in your program and see all the call stack and the state of your program as you hit it, and they don't have to reproduce the problem on their machine. So it's very easy to share. And from the built-in IDE window, where you can actually see the current point in the call stack where the issue occurred, you can actually initiate a live share session and leverage this feature in Visual Studio, where you can collaborate with someone else on a different machine. For example, you encounter this on your machine, and you can invite some other developer into a live share session with you to see this crash and collaboratively debug the issue, and maybe even change the code around and try to on a remote machine. So this is a very, very nice, I think it's a game changer in general, not just in terms of sanitizers. So do think about using snapshot files in Visual Studio. This is how a snapshot loaded might look like. You have the exception dialog box there, where the exception occurred in code. You have the raw data in the output window that is parsed and surfaced in that need to overlay window. And you have the usual suspects, the watch windows and the call stack and everything. So it's very nice way to jump into analyzing issues. So it bootstraps the process of starting an investigation. The rest is on your own. I think, at least for me, finding about how these things works is, at least at the beginning, it felt a lot like magic. So I think a lot of the effort on my part was actually trying to understand how it works behind the scenes and demystifying some of the inner working of the ASAN runtime. So I'll try to share with you some of the stuff I found out, and hopefully eliminate some of the mystery around the ASAN. ASAN is basically just malware used for good. So if you run a program that intentionally does some heap overflow or something, you might have this ASAN report pop up, and you immediately, funnily enough, this actually happens on Windows 10. Windows Defender actually detects this as malware. But basically, the ASAN is in two parts. On the one hand, and the two parts actually collaborate. You have the compiler that does instrumentation of the code, the stack layout, and actually makes calls into the runtime. It basically injects additional code between your code, and it creates metadata in the object file for the runtime to consume. And you have the dynamic part, the runtime, that actually hooks, that's the malware part, hooks calls like malloc, free, memset, and all the usual memory routines, and many others. And it does error analysis and reporting, and it does not require a complete recompile, which is great news for interop. For example, if you have some modules that are instrumented, you can actually load them into projects that are not instrumented and vice versa. There are some caveats, and I'm going to pinpoint some of them here. But in general, it's a very good thing that you don't have to recompile the whole thing like you have to do with memory sanitizer. And it has 0 positives, so what's not to love? Typical Asan report, if we drill down and see how it looks, for example, a heap buffer overflow, we have your call stack there and information about the memory region that was tagged and the issue that is reported. And then you have like a very confusing map, at least at first, if you're not familiar with it, with trying to show you where the problem is in your memory. So you have to try to figure out how to analyze this output and see what it means. You even have a little legend there that actually tries to help you navigate the meaning. And basically, anything that's 0, it's addressable memory. Anything that's a negative byte, negative value, is some kind of issue marker and pinpoints the kind of issue that was detected there. And let's see how it works. Let's say we have the process memory on the left, and it works by building a shadow memory for any allocation that you do. For example, and we call that shadow mapping. So basically, for every allocation that you have, in the shadow memory, you have a mirrored allocation, and around that, we have what we call red zone, and that is poison memory. And that will help detect accesses outside of bounds of proper allocated objects. And let's see a simple example. Let's say we're trying to write through a pointer a value bad food, and very simplified code generation by the compiler that instruments the code injects this additional check where it checks that the P address is actually poisoned or not. Is it bad? And if it's bad, it will report the issue in the console, and it will intentionally crash the application so that the actual store does not happen in the P address, the address pointed by P. So if the shadow byte is poisoned, the application is prevented from actually accessing that part of memory. So that's good. That's a good crash. It doesn't prevent hijacking here. And let's see, and it has to be fast, of course, because if all of this has a big runtime overhead, nobody's going to use it. So usually this whole thing is very, very fast. So this lookup into shadow memory has to be almost instantaneous. And the lookup mechanism is actually very simple. Asan maintains this lookup table where every 8 bytes of your memory are tracked by 1 shadow byte. So basically, the shadow region is basically 1/8 of the address space that you have. And the formula to get to it is actually very simple. You just have a right shift by 3 that's dividing by 8 and adding some kind of offset. That's the location of the shadow memory start. And you have a marker that indicates the kind of access that is detected in that situation, basically the red zone type that you have in that location. In this case, stack use after scope. And the lookup function is very, very simple, almost like this. Checks if an address is poisoned. It does this translation with the offset. That's the location of the shadow memory. And the shadow byte is calculated as previously shown. And basically, if the corresponding shadow byte is non-zero, then the address is poisoned. And the actual code there is the code that needs to be reported. For in this example, F8. So it's very, very fast. And let's see graphically how it might look. It sort of looks like this. So in this case, we're actually accessing within bounds of our allocated memory. So we're trying to write 0x food at location P, and the shadow byte is checked and is okay. It's not poisoned. So then the stored is allowed. But if the access is in a location that is out of bounds of our allocated memory, then it maps to a red zone, and the shadow byte is reported as poison memory, and then the report is triggered, and the application is crashed, and bad food is never written there through P. So pretty simple, I think. But to make this stuff work, the actual ASAN runtime has to do some work to make sure the allocations are done in a proper way, in an orchestrated way. So you can actually mark everything accordingly with the required red zones. So if your regular malloc tries to allocate sequential cells into memory so that it's friendly for locality, ensuring locality and it's cache friendly, your ASAN malloc does things in a totally different way and actually allocates putting intentional gaps within your allocation blocks, so you can mark those as red zones. And in the shadow memory, each gap and the surrounding limits of this buffer are marked with appropriate red zones as poisoned memory. And interesting, as soon as you deallocate an object, so you see here, allocation 3 is deallocated, and when the object is deallocated, its corresponding shadow byte is poisoned intentionally to delay use of freed memory and see if accesses to that location are made and detect them. And it can detect this way heap underflows or overflows or use after free or double frees, stuff like that. So this is very neat. And for stack allocations, for example, we also have stack red zones. So the shadow memory is actually poisoned. The stack is poisoned when the function is entered, and the stack red zones are unpoisoned when the function is taken off the stack. And you have your left red zones, your mid red zones, and right red zones that are indicating different access patterns within the stack. And let's say we have a buffer, a byte buffer, and some integer here on the stack in our function, and we're trying to access the 13th element of this buffer, which is clearly not allowed. And again, the same check is instrumented into our code by the ASAN when compiled. And the ASAN runtime checks if this particular location we're trying to access is poisoned, and in this case, will issue a report and crash the application and does not allow us to actually store that 0 in that 13th location. So basically the same mechanism for the stack. One that's a very, very neat one, and I actually love this one. And this is done with the help of code annotations in the implementations of standard vector in both lib C++ and lib standard C++. Right now, this is not yet in Visual Studio. You have the container overflow. So basically, this check actually tries to figure if you're making an access within the capacity of a vector. So you're within the allocated memory for the vector, but you're clearly out of bounds of the proper value stored in that vector. So you're beyond vector.end. So this is, again, using poisoned memory. All the remaining capacity is poisoned. And if you're trying to do a simple access pattern, like shown in this little code snippet here, you will get a container overflow fired by the ASM runtime. And I'd like to point your attention that the access here is made through an indirection with using this p pointer, because if the access would have been with a subscript operator like v sub 3, then this could easily be detected by simple checks within the vector implementation of the subscript operator. So in this case, using some kind of pointer aliasing, this can only be detected via proper runtime analysis. So this is, again, very nice. And my understanding is that a similar thing is going to be implemented for standard string and standard deck. Not sure exactly on the status of these implementations, but I think this is a very nice check. Like I mentioned when we talked about mapping into shadow memory, this instrumentation needs to be blazing fast. And the average slowdown of an instrumented program is around 2x, which is fantastic. If you're comparing this to other tools before ASAN doing the same kind of thing, this is way of an improvement. We're talking like tools like Valgrind usually are like 10x slowdown on your program. So this is very fast. Now this is all great, and you welcome to try this on your own and play around with it. And you're gonna probably find some stuff that doesn't work, not in terms of false positives, but in terms of things not working for you, or maybe your projects. So I encourage you to play with it, and I'm gonna show you now some stuff that you need to know as you get in, stuff that I've discovered playing around mainly with 16.7 version from this summer, and stuff that's some stuff was improved in 16.8 preview, and some issues are still outstanding, and your mileage may vary, and I do encourage you to kick the tires and find out what works for your projects. And let's see some issues. First of all, compiling and linking from command line is possible, so you can totally do this outside of Visual Studio if you want to, but it's a hassle. So there's a very detailed article there. I put the link on Visual C++ blog. You have to be very careful in choosing the right Asan runtime libraries to link against, because otherwise you're going to get incomprehensible linker errors and stuff will not work. So building from command line, it's possible, but you need to pay attention. The IDE really helps here, and especially with 16.8, it's really an improved experience. So yeah, if you're using and loving edit and continue for debug builds, we're not using it ourselves, but lots of people are loving this feature, and it's actually on by default for new projects. So you're very likely to hit this one yourselves. Asan is not compatible with edit and continue workflow, so you'll have to disable this for debug builds if you're planning to instrument them, at least temporarily, while you do instrumentation and you run Asan. So be aware of this. You'll encounter this as an error. A problem that I alluded to earlier when I talked about interop and partially building and instrumenting different modules of your application is mixing Asan and non-Asan instrumenting modules. For example, if you're building a plugin for an application that you don't control, for example, you're building an Office plugin or an Excel plugin or something, and you don't have control over that application that you're plugging into, there are some issues around the load library. For example, non-Asan built executables cannot call load library on a DLL built with Asan. So the reason is that the runtime needs to be able to track memory that is allocated in the program, and it's the application might do a heap alloc, and the Asan might not be able to track that. So currently, this is a limitation and a big problem if you're building a plugin. But the MSVC team is considering dealing with this issue in a later release, so they are aware of this issue, and we'll try to address it. But at the moment, if you don't control all the parts that you're building, and you're doing some things like this, we're dynamically loading a DLL, this might be an issue. So you have to be aware of it and not be surprised. If you're using runtime checks for debug, we're actually hitting this ourselves. So we're using RTCS and RTC1 in debug builds to catch some of the runtime issues. This is being supported for years now in MSVC. These are not compatible with Asan instrumentation, so you will have to disable this while you do instrumentation of your debug builds. And yes, doing instrumentation of debug builds is a thing, because you might encounter things that are easily understandable on debug builds and might be very, very hard to investigate in release builds. And the other way around. So, yeah. So we had to disable these runtime checks so we can do our experiments. And this might be a harmless warning, but if you're building with 3 warnings as errors, as you should, then this might be a build blocker for you. So it was for us. So be aware of this. And it's not very intuitive that you need to disable this. The warning message is not very, very helpful. There are some missing PDBs from the VSC installer, just to be aware. This will be fixed readily in the preview builds, so don't panic. And they don't block you from actually testing this thing around. It appears that VCASAN and VCASAN dlibs are, and basically the corresponding PDBs are not shipped in the installer, both for static linking and dynamic linking into EXEs. So this should be fixed soon, and it's not a blocker for you to test this around. The VCASAN lib, in case you're wondering, is the library that creates all this metadata that the IDE will parse and consume and supports error checking and surfacing all this nice GUI for the memory dumps in those snapshot files that I mentioned earlier. So all that good things come from this add-on library that helps the VC runtime. There are some linker troubles, and basically, I think this is a poor experience, but it's not a blocker. Things will work, but it might put you off if you see these warnings. This is related to the hooking mechanism I explained earlier, and how these APIs are basically hooked by the Asan runtime. And it might be scary to see these warnings appear at runtime, but at compile time, but you can easily ignore them. And I bet you didn't think you were going to see MFC featured at the conference in 2020, but here I am. If you have MFC applications and you try to instrument them with Asan, yes, you can. You're going to hit some issues again around APIs for memory management that the Asan hooks into, and you're going to see some linker errors that basically are going to stop you in your tracks. This particular example here I'm showing is if you're actually doing a static link to the MFC libraries, as most people do. And the fix is, the workaround is fairly easy. You can basically, for instrumentation purposes, you can temporarily set your MFC application to link to the shared MFC DLLs just for testing with Asan, or easily, I think, you can use this linker switch to force multiple to make the linker accept these multiple definitions and basically suppress this error, and it works. So it's not a blocker. It's a workaround. It's not perfect, but it's a workaround. I think this experience can be improved, and the same thing happens if you're hooking these operators or these memory routines yourself. If you're rolling some custom new and deletes, if you're doing your custom memory allocator, if you're doing anything that might interfere with how the Asan runtime is trying to hook into the memory allocation routines, you're going to see linker errors, and it can be worked around, but it's not a pleasant experience out of the box. If you want to read more, I'm going to highlight these excellent articles by Augustin Popa from the Visual Studio C++ blog. So do check them out. Now, last part, and this is a short one, is about warm fuzzy fillings and the fact that sanitizers are actually empowered by fuzzing, so you can automate generating inputs for your program to make it crash. Short case study that was presented at CPPCon this year, a case study at Microsoft scale. So you can see here what Microsoft scale looks like. Scary. And this, you see basically the vulnerability discovery funnel and how dynamic analysis fits into this pattern, and how Microsoft actually runs this stuff at scale, at Windows scale. Again, like I mentioned, Windows CVEs, the bulk of these issues are due to memory safety, and 80% of the Microsoft estimates that 80% of the cases with CVEs around memory allocation are actually found with fuzzing. So yeah, definitely worth investing into this. The workflow should be like compile and instrument with Asan, run fuzzing, and recompile with different inputs. Again, run fuzzing, recompile, run fuzzing, different inputs until you actually hit stuff and record and collect issues and tackle them at scale. And it wouldn't be a 2020 talk without mentioning some cloud stuff. And of course, Microsoft has the Microsoft Security Risk Detection Service, and this has a component of actually leveraging fuzzing in the cloud in Azure. And basically what happens behind the scenes, and this stuff is done automatically for you by the IDE, so it should be always transparent as long as you're an Azure client. You can compile and basically distribute all this work of instrumenting on virtual machines in Azure data centers and run various inputs automatically by Microsoft libfuzzing framework, and collecting the crash results on the failing machines and aggregating the snapshots, those mini dump files that I mentioned earlier, and relaying that information back to the IDE for processing. And you can even initiate a live debugging session from your IDE on your machine, on your laptop, into the VM in Azure that actually hits the problem and debug it right there on the exact point where it was left off in that snapshot. So very powerful. I haven't had the chance to play with this, but I really want to. So this looks like the future of fuzzing for me. So fuzzing at scale. I like millions of fuzzing sessions for your program. Very recent announcement, literally from last week, Microsoft OneFuzz is a platform that will allow you to download. You cannot download it from GitHub. It's an open source platform, and you can run fuzzing jobs on premise or in Azure, like I mentioned earlier. So this is an open source effort. It was announced last week at CPPCon in this session. I do recommend that you watch it as soon as it becomes available on YouTube. It's a very, very interesting session. I really loved it. So this is Project OneFuzz, a self-hosted fuzzing as a service platform. So basically, it tries to make this as easy to access as possible, either to use it yourself or as a service for one-click thing through Azure. You can check out the project here. It's open source since last week. It integrates very nicely with build pipelines. For example, if you're using Azure DevOps pipeline, or if you're using GitHub Actions, it integrates very nicely with these things. It can surface crashes via Teams or via IDO work items. So it integrates in whatever workflow you might be having, and you can access a dashboard like this where you can see the progress of your fuzzing jobs, and you can see the problems that are reporting, and go navigate to those VMs and investigate these issues. And basically all the heavy lifting, if you don't want to play around with it and build your custom in-house infrastructure around fuzzing in your company, you can basically move all that heavy lifting into the Azure cloud. And with this, I hope you're now as excited as I am for leveraging the power of Asan on Windows. And I'm really enthusiastic on bug fixing the stuff we found, we're going to find around this. And we already found some stuff, and I'm sure we're going to hit a lot more things as soon as we start deploying fuzzing at scale in our projects. So thank you very much. And I'm ready to take questions now.